Good day, this is Professor Will, CBMD PhD. Today's Saturday, May 30th, 2020. It is 6:41 2 seconds AM Eastern Standard Time, and this is a continuation of my educational series and lecture on biophysics. So let's get started here. Absorption chromatography. This technique separates the sample into its components based on the degree of their absorption by the absorbent and on their solubility in the solvent used. Silicic acid, silica gel, aluminum oxide, calcium carbonate, and cellulose may be used as a stationary phase in this method. The optimum combination of absorbent and eluting solvent will depend upon the type of sample separation under consideration. For example, hydroxyapatite calcium phosphate is used for DNA separation, as this absorbent can bind double-stranded DNA but not single-stranded DNA or RNA. Normally, any organic solvent can be chosen as the mobile phase, e.g. hexane, heptane, propanol, butanol, etc. Partition chromatography. There are two types of partition chromatography: A. Liquid-liquid chromatography. In this type of partition chromatography, the material separation is achieved based on its differing solubilities in two immiscible liquid phases. The sample is dissolved in a relatively nonpolar solvent and is passed through a column that contains immobilized water or some other polar solvent in a supporting matrix such as silica gel. When the sample moves through the column, it gets partitioned between the mobile phase and the immobile polar phase. In the reverse phase liquid-liquid chromatographic method, the stationary phase is a nonpolar substance like liquid paraffin supported by the matrix. High-performance liquid chromatography, HPLC, is a liquid-liquid partition chromatographic technique. It is widely used for the separation of biological compounds, either as a normal phase method or as a reverse phase method. In the latter, it is useful for separating polar compounds, be countercurrent chromatography. The sample is equilibrated between two immiscible solvents, e.g. ethyl acetate and water, in a test tube. The partition coefficient is defined as K equals concentration C sub 1 in the upper phase divided by concentration C sub 2 in the lower phase. After equilibration, the upper phase is withdrawn and transferred to a fresh volume of lower phase. Solvent in another test tube. Absorption is a process by which a substance is absorbed on the surface of another. There is almost no penetration beyond a few molecular layers. The original lower phase is added to a fresh volume of upper phase solvent, and so on. The process is repeated several times, yielding several test tubes, half of them finally containing the upper phase solvent and half containing the lower phase solvent. A solute which is more soluble in upper phase, K is greater than 1, will concentrate in tubes containing the upper phase solvent. If the solubility is greater for lower phase, K is less than 1, then it will concentrate in tubes of the lower phase solvent. Countercurrent chromatography is successfully used for cell organelle fractionation. Gas-liquid chromatography, GLC. The two phases used are a liquid and a gas. The method is very sensitive and reproducible. The partition coefficient of a volatile sample between the liquid and the gas phases, as it is carried through the column by the carrier gas, may be largely different from unity. This feature is exploited to separate or purify the compound. Stationary or immobile phase is generally non-volatile and thermally stable at the temperature of the experiment. Usually organic compounds with high boiling point are coated on the base to form the stationary phase. The base is generally made up of sealite diatomaceous silica. The sample to be separated is packed in a narrow coiled steel or glass tube and placed in an oven at an elevated temperature. An inert gas like argon, nitrogen, or helium is passed through the tube. The sample is volatilized and is carried away by the mobile phase. It is passed over the solid phase, packed into another column, and as it does so, the sample distributes itself between the gas and the solid phases. Many biological samples like amino acids and proteins have ionizable groups. The samples can therefore be separated based on the net charge acquired by them at a certain pH. An ion exchanger is a resin and can be either a cationic exchanger or an anionic exchanger. The cationic exchanger has negatively charged groups and attracts positively charged molecules. An anionic exchanger has positively charged groups and attracts negatively charged molecules. Commercially available ion exchangers are made by copolymerizing styrene with divinyl benzene. Two materials become cross-linked, with the permeability of the resin varying with the degree of cross-linking. When this insoluble cross-linked resin is placed in water, a network of charged groups is formed. When the sample suspended in the liquid phase comes in contact with the resin, the charged groups in the sample replace the charged ions on the surface of the resin, and the sample becomes strongly bound to the resin. As an example, suppose that the sodium salt of a strongly acidic resin, which contains SO sub 3, groups is placed in a suspension. Normally the Na positive ions would be bound to the negative sulfate groups in the resin. However, on exposure to the sample, the positively charged groups present in the sample may displace some of the Na positive ions from the surface. This exchange of ions at the exchange site leads to the distribution of the sample between the solid and liquid phases. The higher the charge on the molecules to be exchanged, the tighter it binds to the resin. At low pH and salt concentration, most amino acids will firmly bind to the resin by the following reaction. RSO sub 3 repeated ellipse Na positive plus N positive H sub 3 R transpose. RSO 3 repeated ellipse N positive H sub 3 R plus Na positive. The last step in the separation procedure is to elute the bound molecule from the resin by reducing the attractive force between the resin and the charged molecule. This is achieved by changing the pH or the ionic concentration, or by affinity elution. In affinity elution, an ion with greater affinity than the bound molecule is introduced into the system. If more than one type of molecule is bound to the column, a stepwise elution can also be done by using a second solvent, a third solvent, and so on. A widely used matrix medium for ion exchange chromatography is DEAE cellulose column, in which the diethyl aminoethyl group acts as an exchanger. Cellulose fibers, polyacrylamide gel, cross-linked dextrin, also known as Safadex, are other common materials used as the matrix. Molecular exclusion chromatography. The separation of samples based on their molecular weights is known as molecular exclusion chromatography. MEC. Gel filtration and molecular sieve chromatography. The matrix for MEC is made up of polyacrylamide, Safadex, or agarose gel. Polyacrylamide and Safadex are supplied in the dehydrated form. When soaked in the solvent, they take it up rapidly and swell up, forming a slurry. When this slurry is used for packing a column, pores of uniform size are formed by the gel and are used for separating the sample according to their molecular size and shape. A column of gel, the porous material, is kept in equilibrium with a suitable solvent in which the molecule to be separated is dissolved. Large molecules in this solution are excluded from the pores and pass through the interstitial space, reaching the bottom of the column quickly. Smaller particles penetrate through the pores of the gel and are distributed in the solvent inside as well as outside the molecular sieve. Smaller molecules are thus retarded and reach the bottom at slower rate. For a given sample, the distribution coefficient, K sub D, is dependent upon its size. If the molecule is completely excluded by the sieve, then K sub D equals 0, whereas if it penetrates the gel and has accessibility to the inner solvent, then K sub D equals 1. For all other intermediate sizes, the K sub D value will lie in the range 0 to 1. The chromatography column consists of loosely packed resin particles. V sub T is the total volume of the column. It is made up of three terms. 1. The void volume, V sub 0, or the volume of the exterior solvent. 2. V sub G, or the solid volume of the gel particles. Number 3. V sub I, or the internal volume of the pores that are accessible to the solvent. V sub T equals V sub 0 plus V sub G plus V sub I. The eluting volume is the volume of the solvent that must flow through the column before a particular solute emerges. This is given by the equation V sub E equals V sub 0 plus K sub D V sub I. A solute that is completely eluted will have K sub D equals 0. Therefore, V sub E equals V sub 0 for such a sample, i.e., the eluting volume is equivalent to the void volume. But a solute that can enter the pores will have to displace an additional volume given by K sub D V sub I. Partition coefficient K sub D can be determined from this equation if the elution volume V sub E is measured. V sub 0 and V sub I are determined prior to the start of the experiment and are constant for a given volume. Good day, this is Professor Will, CBMD PhD on infectious disease, biophysics, and microbiology. Well, hope you enjoyed listening. Until next time, have a great day.